There is a planet in our solar system that scientists have visited exactly once, studied with a handful of telescopes, and largely set aside in favor of flashier neighbors. It sits out there, rolling quietly through the dark, tilted nearly on its side, colder than any other world in the solar system, wrapped in rings so dark they border on invisible. It has secrets baked into its core from a catastrophic collision billions of years ago. Its magnetic field behaves in ways that still do not have a complete explanation. And yet, when people list the planets worth getting excited about, this one rarely makes the cut. That planet is Uranus. What we are actually here to talk about is one of the most scientifically strange and criminally underappreciated worlds in the entire solar system. Over the next several minutes, we are going to walk through everything we know about Uranus, revisit the single fleeting mission that gave us most of that knowledge, and then dig into a remarkable wave of new discoveries that have accumulated in recent years. Some of these rewrite what we thought we knew. Others open questions we are not yet equipped to answer. All of them point toward the same conclusion: we need to go back. The story of Uranus begins not with a space agency, not with a rocket, and not with any kind of deliberate hunt. It begins in a back garden in Bath, England, in 1781, where an amateur astronomer named William Herschel was scanning the sky with a telescope he had built himself. He noticed an object that moved slightly against the background of fixed stars over successive nights. He initially thought it was a comet. It was not. It was a planet, the first ever discovered using a telescope, and it effectively doubled the known size of the solar system overnight. Herschel wanted to name it after King George III. The astronomical community eventually settled on Uranus, after the Greek god of the sky, following the convention already established for Jupiter and Saturn. It is the only planet name drawn from Greek mythology rather than Roman. Since that discovery, only 2.5 Uranian years have gone by. Each one lasts 84 Earth years. The planet is currently approaching a northern summer solstice in 2030, meaning its north pole has been tilting progressively toward the sun for decades. This matters enormously for what we observe there, and we will come back to it. For most of its recorded history, Uranus was little more than a faint greenish disk in telescope eyepieces. 5 moons were identified before the 20th century. A ring system was found by accident in 1977, when astronomers noticed a star blinking out in a regular pattern as Uranus passed in front of it. The star was dimming not just once, but several times on either side of the planet. Something was orbiting it in rings, but details remained frustratingly out of reach. The planet was simply too far away. Then, in January 1986, everything changed. Voyager 2 was launched in August 1977 and spent nearly a decade crossing the outer solar system. It had already visited Jupiter and Saturn before locking onto its trajectory toward Uranus. On the 24th of January 1986, it made its closest approach, swinging within 81,500 kilometers of the planet's cloud tops. The entire close encounter, the period of useful scientific observation, lasted only a matter of hours. Then the spacecraft continued on its way toward Neptune, and eventually out of the solar system entirely. In those few hours, an enormous amount was learned. Voyager confirmed that Uranus was significantly colder than theoretical models had predicted, with cloud top temperatures reaching as low as -224 degrees Celsius. That is not just the coldest point on Uranus, it is the coldest temperature measured on any planetary body in the solar system. Scientists had expected Uranus to radiate more internal heat into space. It does not. That anomaly immediately became one of the defining mysteries of the planet. Voyager also found a magnetic field unlike anything previously encountered. It was tilted by nearly 60 degrees relative to the planet's rotational axis and offset significantly from the geometric center of the planet. This is deeply unusual. On Earth, Jupiter, and Saturn, the magnetic field more or less aligns with the spin axis and originates near the core. On Uranus, neither of those things is true. The mission added 11 new moons to the catalogue and confirmed the ring system in detail. Then it was gone. For the next 4 decades, that single fleeting visit formed the backbone of nearly everything we knew. No follow-up missions were sent. Uranus became, in the blunt language of planetary scientists, one of the least explored objects in the solar system. On the surface, or rather in the upper atmosphere, Uranus presents itself as a serene, uniform blue-green sphere. That color comes from methane, which makes up roughly 2% of the upper atmosphere alongside hydrogen and helium. Methane absorbs the red end of the visible spectrum and reflects blue-green wavelengths back to our instruments. Underneath that calm exterior, however, the structure of Uranus is a subject of genuine scientific controversy. The traditional model describes Uranus as an ice giant, with a small rocky silicate core at its center, surrounded by a deep mantle of water, ammonia, and methane in compressed fluid states. The word ice is somewhat misleading here. At the pressures and temperatures found deep inside Uranus, these compounds exist in exotic phases that have very little in common with the ice cubes in your freezer. Temperatures in the deep interior may reach close to 5,000 degrees Celsius. Pressure at the base of the mantle is estimated at hundreds of gigapascals. Under those conditions, methane molecules can be torn apart, with the liberated carbon atoms compressed into crystalline structures. In other words, the interior of Uranus may be raining diamonds. That picture, compelling as it is, has recently been challenged. Research published in 2025 by scientists at the University of Zurich took a fundamentally different approach to modeling the interior. Rather than starting with assumptions about composition, the researchers generated large numbers of randomized interior models and then filtered them against actual observational data to see which ones remained plausible. The results were striking. The range of viable compositions turned out to be far wider than previously assumed. At one extreme, the rock-to-water ratio could be remarkably low, making Uranus essentially a vast ball of fluid water with minimal rocky content. At the other extreme, the ratio could be so high that Uranus is primarily composed of rock. That second scenario would reclassify Uranus entirely, from an ice giant to something more accurately described as a rock giant. And if that turns out to be correct, it creates serious problems for our standard models of how planets in the outer solar system form. Those models assume a particular abundance of volatile ices at large distances from the Sun. A predominantly rocky Uranus does not fit comfortably within that picture. The honest answer, as the researchers themselves noted, is that we cannot distinguish between these possibilities without significantly better data. We need to go back. One of Voyager 2's most lasting impressions of Uranus was of a planet with remarkably little going on atmospherically. Compared to the churning bands and massive storm systems of Jupiter, Uranus looked almost blank. A few faint cloud streaks, a dark spot here and there, nothing dramatic. This reinforced the perception of Uranus as a passive, featureless world. Ground-based observations over the decades since have dismantled that impression entirely. In 2014, astronomers using the W.M. Keck Observatory in Hawaii tracked a series of major storms erupting in the northern hemisphere of Uranus. 8 significant storm systems were identified during a single observing campaign. The largest of them, visible in near-infrared imaging, was the brightest storm ever recorded on the planet at that wavelength. It was bright enough to be tracked by amateur astronomers using consumer-grade equipment, which was genuinely unprecedented. The storm reflected such a substantial fraction of the total light coming from the planet that it was functionally impossible to overlook. The Hubble Space Telescope has been monitoring Uranus across a span of more than 2 decades, building a long-term record of atmospheric change. A major study, published in 2025, examined what happens to Uranus as it progresses through its extreme seasons. The observations covering the period from northern spring through the approach of northern summer found a clear and dramatic pattern. The North Pole darkened during the equinox and then brightened significantly as the sun climbed higher in the northern sky. Aerosol layers in the upper atmosphere thickened substantially at the northern pole, turning it from a dark, absorptive region into one of the most reflective areas on the planet. Meanwhile, the South Pole, sinking into a decades-long winter, darkened correspondingly. This pole-to-pole swap in brightness and atmospheric thickness is being driven directly by sunlight, which is structuring the chemistry and physics of the atmosphere in real time. Uranus, uniquely among all the planets, receives more solar energy at its poles than at its equator. That is a consequence of its extraordinary axial tilt, and it drives atmospheric circulation patterns unlike anything seen elsewhere in the solar system. Interestingly, a team based at Imperial College London established that Uranus's upper thermosphere is also being heated by the solar wind, not by the sun's light. This appears to be unique to Uranus, and because solar wind pressure has declined measurably since around 1990, Uranus has been gradually cooling in its thermosphere as a result. To understand why Uranus is the way it is, you have to go back about 3 to 4 billion years, to a time when the outer solar system was a considerably more violent neighborhood than it is today. Massive protoplanets were still migrating, colliding, and scattering debris across vast distances. Uranus was among the bodies taking shape during this turbulent period, and at some point during that formation, something very large hit it. The evidence for this collision is written into the planet itself. That near horizontal tilt of 97.77 degrees does not happen naturally through gradual orbital evolution. Something knocked Uranus onto its side. High-resolution computer simulations published in the Astrophysical Journal in 2018 modeled more than 50 different impact scenarios in an attempt to reproduce the specific characteristics of Uranus as we observe them today. The simulations converged on a scenario in which a rocky, icy protoplanet, approximately 2 to 3 times the mass of Earth, delivered a glancing blow to the young Uranus. The entire event would have been over in a matter of hours. Enormous as it was, the impactor did not shatter Uranus or scatter it from its orbit. Instead, it dumped its energy deep into the planet's interior and tilted it permanently. The consequences of that event cascade through nearly every anomalous feature of Uranus. The impactor's material was deposited in the deep interior, creating what the simulations describe as a high-entropy, thermally disordered shell within the planet's icy mantle. Materials in that disordered high-entropy state are poor conductors of heat. That shell effectively acts as a thermal blanket, trapping the residual heat from formation deep inside and preventing it from reaching the surface. This is the leading candidate explanation for the single most puzzling fact about Uranus: why it emits so little heat. 2 studies published in 2025 confirmed that Uranus does emit somewhat more energy than it receives from the Sun, but only about 15% more. Neptune, by contrast, emits more than twice its received solar energy. That gap between the 2 neighboring ice giants is enormous, and the internal insulating shell, left by a primordial impact, is currently the best explanation available. That same collision also shaped the moons. At the time of impact, the major moons of Uranus had not yet fully formed. They coalesced afterward from a disk of material around the planet, and Uranus's new axial orientation locked them into orbits that are perpendicular to their neighbors in the solar system. All 5 major moons orbit in the same extreme tilted plane as the planet's equator. Magnetic fields are generated deep inside planets. On Earth, the motion of liquid iron in the outer core drives a dynamo that produces our global magnetic field, oriented more or less along the planet's spin axis. Jupiter and Saturn follow the same pattern. Uranus does not. Voyager 2 detected a magnetic field tilted nearly 60 degrees away from the rotational axis, originating from a point offset significantly from the center of the planet. The resulting magnetosphere is fundamentally asymmetric. Its magnetic tail, stretched out behind the planet by the solar wind, does not flow in a clean sheet. Instead, it corkscrews through space for millions of kilometers because the entire magnetic structure rotates off-center as Uranus spins. When Voyager made its measurements in 1986, the magnetosphere appeared unexpectedly small and compact. This confused planetary scientists for decades because the readings seemed inconsistent with the scale of the planet generating them. A reanalysis of the original Voyager data, led by researchers at NASA's Jet Propulsion Laboratory and published in Nature Astronomy in 2024, finally provided a resolution. The timing of Voyager's visit coincided with a period of intense space weather. A powerful solar event had compressed the magnetosphere inward at precisely the moment the spacecraft was measuring it. The actual magnetosphere of Uranus, free from that transient distortion, is in fact substantially larger and more dynamic than those initial readings suggested. The origin of the magnetic field itself remains unresolved. The leading hypothesis is that the dynamo generating it does not reside in the core at all. Instead, it may be produced by convective motion within the planet's icy mantle, with the unusual composition and structure of that mantle shaped significantly by the ancient impact, producing a field with its peculiar off-axis, off-center character. There is one genuinely beautiful consequence of all this magnetic strangeness. Because the magnetic field does not align with the poles, the auroras on Uranus are not confined to the polar regions the way they are on Earth, Jupiter, or Saturn. They can appear almost anywhere across the planet's disk. These sprawling, diffuse auroral displays were imaged by Hubble in both visible and ultraviolet light, and after 30 years of effort, infrared auroras were finally detected in 2023 using the Keck 2 telescope. Scientists studying a decade's worth of auroral imagery recently used the movement of these features to calculate Uranus's rotation period with exceptional precision. The result: 17 hours, 14 minutes, and 52 seconds per full rotation, approximately 28 seconds longer than Voyager 2's original estimate. At the time of Voyager 2's flyby, 5 moons were already catalogued: Miranda, Ariel, Umbriel, Titania, and Oberon. These 5 major moons bear names drawn from characters in Shakespeare's plays and Alexander Pope's poetry, a naming convention that distinguishes them from every other moon system in the solar system. The Voyager encounter added 10 more to the list. Telescopic surveys in the following decades pushed the tally higher still, and it has continued to climb. Uranus currently has 29 confirmed moons. The 28th, designated S/2023 U1, was discovered in 2023 by astronomer Scott Shepard using the Las Campanas Observatory in Chile. The 29th and most recent edition was identified in February 2025 using data from the James Webb Space Telescope's near-infrared instrument, catalogued as S/2025 U1 and awaiting official naming by the International Astronomical Union. The tradition of naming Uranian moons after literary characters leaves plenty of room for creative suggestions. Beyond the sheer count of moons, recent work on the Major 5 has raised some genuinely provocative possibilities. Studies published in 2025 modeled the internal structures of Miranda, Ariel, Umbriel, Titania, and Oberon in detail, incorporating updated understanding of how heat is retained and distributed in icy bodies over geological time. The findings suggest that these moons may harbor differentiated interiors with distinct rocky cores, intermediate layers of mixed material, and outer shells of ice. More intriguingly, the models indicate the possible presence of liquid water oceans sandwiched between the rocky and icy layers, maintained in a liquid state by residual radiogenic heat or tidal effects. If any of those moons do contain liquid water beneath their icy surfaces, the question of habitability follows immediately. We do not know the answer. We cannot know without sending hardware there. Uranus has rings, and they are remarkable in ways that receive very little attention. The ring system orbits in alignment with the planet's tilted equatorial plane, which means that when Voyager approached in 1986, the rings were facing the spacecraft nearly head-on, creating a striking bullseye appearance in the imagery. 13 distinct rings have now been catalogued, most of them narrow and sharply defined, ranging from a few kilometers wide to around 100. The most distinctive property of the Uranian rings is their color, or rather the near-total absence of it. They are exceptionally dark. Their albedo, a measure of reflectivity, sits below 2%. That makes them the darkest material of any natural feature in the solar system. The composition of this dark material is not definitively known. The leading hypotheses involve water ice particles coated or mixed with organic compounds, or methane ice that has been irradiated and chemically altered over time into dark carbonaceous material. Against the bright backdrop of the planet itself, these rings are genuinely difficult to detect in casual observations. The narrowness of many of the rings presents its own puzzle. Ring systems tend to spread out and disperse over time due to gravitational interactions and particle collisions. Something must be containing some of these narrow rings, and the leading candidate mechanism is the influence of small shepherd moons orbiting on either side of individual rings and gravitationally confining the particles within them. Evidence for this exists in a few cases, but for the majority of the narrow rings, the confining mechanism remains unclear. In April 2025, a rare stellar occultation gave scientists a powerful new opportunity to study the ring system. Uranus passed directly in front of a star, roughly 400 light-years away, and for approximately an hour, an international team of more than 30 scientists coordinating 18 observatories simultaneously monitored the event. It was the largest coordinated observation of Uranus since Voyager 2 made its pass 4 decades earlier. The precise timing of each ring's occultation of the background star allowed scientists to refine Uranus's exact orbital position by hundreds of kilometers, critical data for planning any future spacecraft trajectory. Atmospheric results from this campaign are still being processed, but the orbital precision it delivered is already feeding into mission planning. And this is only the beginning of a favorable observational window. Over the coming decade, Uranus will transit across the background of the galactic center, producing conditions ideal for further occultation campaigns. The best opportunity in that window arrives around 2031, when alignment conditions will be better than anything seen in recent memory. For all that has been learned about Uranus through telescopes and reanalyzed archival data, the gaps in our knowledge remain fundamental. We do not know what the planet is actually made of. We do not know why its magnetic field behaves the way it does. We do not know whether its moons hide liquid oceans. We do not know what those dark ring particles are composed of. We cannot answer any of these questions from Earth. We need to go back. That case has now been made at the highest levels of the scientific community. The 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, the document that sets NASA's strategic priorities for an entire decade, placed a Uranus orbiter and atmospheric probe mission at the top of its list of large strategic missions. This is not a minor endorsement. The Decadal Survey is produced after years of community input and rigorous evaluation. Uranus being named the top priority represents a sea change in how the planetary science community values this world. The mission concept being developed would send a spacecraft into orbit around Uranus rather than simply flying past, allowing sustained observation over multiple years. An atmospheric probe would descend into the cloud layers and transmit data as it fell, directly measuring composition, temperature, and pressure at multiple altitudes. The orbiting spacecraft would map the magnetic field in detail over time, observe the weather systems and atmospheric dynamics through a full season, characterize the ring structure, and make close passes of the major moons to assess their surface compositions and potential interior oceans. Timing is everything. Orbital mechanics offer a narrow and enormously valuable window in the early 2030s. A spacecraft launched during the 2031 or 2032 window could receive a gravitational assist from Jupiter, which significantly reduces both travel time and fuel requirements. A launch that misses this window faces a considerably longer journey and higher costs. Whether funding will be secured and a mission formally approved in time to meet that window remains an open question, but the scientific case has never been stronger, and the institutional momentum has never been higher. The Chinese National Space Administration has also proposed a mission to Uranus, designated Tianwen-4, adding an international dimension to the renewed interest in the outer solar system's most overlooked world. When Herschel peered at that faint-moving disk in 1781, he had no way of knowing what it was or what it would eventually reveal about the architecture of the solar system. When Voyager 2 made its brief pass in 1986, scientists had 12 hours to gather what data they could before the spacecraft vanished into deeper space. For the 40 years since, astronomers have worked patiently with those 12 hours of close data, supplemented by what powerful telescopes from the ground and in orbit could contribute. The picture that has emerged is of a planet that is strange, complex, dynamic, and deeply revealing about planetary formation in general. The mystery of the missing heat, points toward a violent history of impact and insulation. The off-axis magnetic field hints at a dynamo structure unlike anything in the rest of the solar system. The possibility that Uranus is primarily rocky rather than icy challenges our standard models of outer solar system formation. The possibility that its major moons harbor subsurface liquid water raises questions that belong to astrobiology as much as planetary science. And the extraordinary behavior of its atmosphere under the influence of the most extreme seasons in the solar system represents a natural laboratory available nowhere else. Every finding highlighted here points in the same direction. Uranus is a world that rewards scrutiny. It has been undervalued and understudied for decades, but the community of scientists who study it have chipped away steadily, using limited data creatively, and what they have revealed is genuinely extraordinary. The next chapter, with a dedicated orbiter, an atmospheric probe, and years of sustained close observation, has the potential to rewrite entire sections of planetary science. The launch window is opening. The science has never been clearer. The question now is whether we will be ready to take it.